population and sea level rise. And we know that sea level rise in combination with groundwater pumping can cause saltwater intrusions in coastal aquifers, rendering groundwater wells unusable and increasing costs for water treatment facilities. It can also impact coastal infrastructure and mobilize urban contamination. So in this panel, we're going to think a little bit about the scientific advances in terms of measuring local level risks of saltwater intrusions, their link to coastal and inland water quality, and then policy options for managing this risk. And although this is a topic that I personally don't know a lot about, I'm very interested in the measurement technologies. And I think with our partnership with JPL, I think it's really important that the last two Earth science missions that NASA has launched, the Surface Water Ocean Topography mission, and we heard about PACE earlier today, really going to address this problem. And we heard from both Kelly and Kate earlier today about the importance of remote sensing. So it's my pleasure we'll have three presentations in this panel, and then we'll have a bit of a discussion. So first we'll have Rebecca Epanchin-Niell, Associate Professor of Agriculture and Resource Economics at the University of Maryland and Senior Fellow at Resources for the Future. Becky's research is at the intersection of economics and ecology to think about decision-making regarding natural resources and ecological systems, and she's thought a lot about coastal adaptation in rural areas due to climate change. We have Shellie Habel here as a research specialist at the School for Ocean and Earth Science and Technology at the University of Hawaii, and her works really span basic science, thinking about coastal morphology, but also sort of coastal impacts. And if people haven't seen it, I'd recommend Shelley's nice review paper that came out on this topic earlier this year. And then finally, Ben Hamlington is here from JPL. He's a research scientist in the Sea Level and Ice Group. And Ben has thought a lot about sea level rise on a range of different timescales, interannual to decadal, and even going back to changes in the last century using historical data, and thinking about how sea level responds to both natural and anthropogenic forcing, and what this means for coastal populations. So I'm really excited to hear these presentations and the conversation to follow. So Becky, would you get us started, please?
Feel free, anybody who needs to stretch your arms, always good to do that in the middle of a session. All right, let me get this. All right, here I'm just gonna real quickly, I have a different, let me just slide this down here real quick, because I think, sorry, there is, I had done an update, but this is not the update, but I'm just gonna move one slide real quick, and then we'll go. Oops, if it'll let me, oh, enable editing. Sorry, one sec. All right, that should do, close enough. All right. All right, there we go. So as I was introduced, I'm an economist, but I work a lot at that intersection of ecology, natural science, and economics. And in a lot of my work, I'm working across disciplines, both with natural scientists, other economists, other social scientists, but also really try to bring in different stakeholders, working with state agencies, working with farmers, working with local NGOs, trying to help inform the research that I do. And that's pretty true of this aspect of my research, where we're looking at saltwater intrusion, trying to understand the causes and consequences, in particularly focused in rural coastal areas. And the research I'll mostly be talking about is in the context of agricultural lands. And so, saltwater intrusion, it's great going a little later in the day because a lot of these topics get introduced, but what we're thinking about here is essentially the introduction of marine salts into freshwater systems, whether you can think about this as coming into, for example, aquifers or groundwater, or we can also think about it infiltrating into surface waters and soils. So, and this is, I want to talk a little bit about some of the different causes of saltwater intrusion and the ways in which the salinity in these coastal areas is often being driven by the combination of changing climate conditions, historic context, and current management of these systems. So we can think about sea level rise. Obviously, we've talked about this before, that as sea level is rising, you have greater forcing of salt water in these coastal areas. Salt water can reach further up the freshwater estuaries. If you're doing pumping from the aquifer, it's less pressure to keep the salt water out. It also interacts with, for example, storms and tides, where as you have higher storms can push that salt water further inland, so contributing to that overwash of salinity. Drought. When we have drought, we have less fresh water coming into these systems. creating that pressure again that keeps the salt water further offshore. Water management, I think we'll be hearing a lot more about this where across the different sessions, where how we manage water, whether it's withdrawals of surface water or withdrawals from the aquifer, that's going to affect essentially the pressure that's going to keep that salt water offshore. But in addition, we have connectivity. So if we think about across a lot of coastal areas, see this, I work a lot on the East Coast, that a lot of the ditching and canals, whether it's to move water to sites, but in particular to help drain water off of sites, those now are these natural conduits. As sea levels rising, those are conduits for the salt water to come further inland. So you've got these mixture of different contextual factors that are affecting susceptibility to saltwater intrusion. That's resulting in changes in the biogeochemistry. That's why, making water, you can't drink it, it's bad for your health, but it's also changing the chemical composition of water affecting crops, but also the soil chemistry. So a lot of the work that I do is looking in these more natural systems contexts where we're thinking about the impacts upon different ecosystems, whether you think about ghost forest formation, essentially these areas that are being impacted by salts, you're not having recruitment of new trees. Trees eventually are dying off, combination of salinity and inundation, so you have loss of these coastal forests. You also have promotion of some species invasions, particularly of salt-tolerant species, which maybe otherwise would not have been spreading in these systems. Crop yield declines, so most of the crops we grow here, particularly in the US, are not salt tolerant, and so we're seeing changes in agricultural productivity in these coastal areas. You see this also in the case of irrigation in arid areas where you have the buildup of the salts. Eutrophications, this kind of tying back into our first session or second session today. One of the things that salinization can do in these soils, particularly when you're thinking about in these agricultural areas, is it actually contributes to mobilization of nutrients. So it can exacerbate some of the water quality issues that we may already have in these locations, particularly when you have areas being affected by salts that otherwise, that have long legacy nutrients within them. And then also this is tied to marsh migration. We're thinking about sea level rise. We're thinking about where wetlands are being drowned on the lower end. They're needing to move further inland in order to maintain those salt marshes for the habitat. The changing in salinity affects how those transitions occur, as do the land use decisions in these affected areas that determine whether or not those will be areas accepting of future marsh conditions. So much of my work, if you use this figure here is of sort of the mid-Atlantic area, the red showing some projections for future sea level rise. A lot of this area is very low-lying, and this here is, actually I think we looked at some of this data, or heard about some of this data earlier, so we did all predictions of future sea level rise in our local Chesapeake Bay area, and this here is just from 1990 to 2020, looking at changes in sea level in this area. And so this is an area with high rates of sea level rise, high rates of subsidence. It's low-lying coastal plain in a lot of areas, and also an area with a lot of focus on the water quality challenges. And in addition, we have a lot of agriculture in the area, which is being impacted by saltwater intrusion. So this here is a drone image of some of the coastal area here along the eastern shore of the Chesapeake Bay. And as you can see, a lot of agricultural land very close to the estuarine system. Obviously that ties into the access of nutrients into that system, but also it's affecting the salinity levels. For example, this here is a cornfield, and these areas are all areas where the corn has died and is not flourishing due to salinization. So we've actually gone in and taken soil samples across this, trying to understand the elevational gradient associated with the salinity impacts in that area. Also harder to see, you have areas where you can see some of the trees dying off, and here's a lot of the wetland that is expanding into the area. This here is another image just of another agricultural field. This here is essentially a salt crust across this. It's no, there's some very sad-looking soy far in the back end of that figure, and you have these marsh grasses moving in. So in my research, we've been tackling a number of different issues. I was just going to touch on two of them. One is there's been a real call when we're talking to the farmers, when we're talking to the NGOs, when we're talking to the state planning agencies, where is the saltwater intrusion happening, and how is it likely to progress into the future? You know, the NGOs that we're working with, for example, are trying to figure out what kind of advice should they give to the landowners that they're working with who are beginning to see saltwater intrusion. What is that time period where they're going to have to be able to adapt and transition with these influences? Essentially, we have the saltwater intrusion being the sort of leading edge of sea level rise, where you're seeing the impacts from the salinity, oftentimes well before you're seeing the impacts of inundation. So we've been tackling this. We have kind of two different approaches that we've been taking. So one, Dr. Mondal at University of Delaware, we worked to use remote sensing, trying to use freely available remote sensing data to be able to map salt patches on these agricultural fields. So here you can see an example of the agricultural fields, and then using the spectral information, not my expertise, she was able to map a lot of to map at the 1 meter scale these salt patches across the Delmarva Peninsula. And based upon that, we can look at, she had two different time periods, and we can look at how changes in the extent of these salt patches across the two time periods. We can see a 93% increase in the amount of affected farmland due to these salts. We also saw over 8,000 hectares of agricultural land convert to marsh just in that time period. And so, you know, looking then again, just kind of putting a rough economic value associated with that, we can see an approximate loss of profits on those areas from about $40 to $107 million in that Delmarva Peninsula area. So one of the things, this kind of came up earlier, this here is a snapshot across 2 periods of time where we have information. The one question is, well, what's going to happen in the future? And so for that, we've actually been actually going out and taking soil cores across a lot of the eastern shore and then relating that to various imagery, various information data on different soil types and topography using LiDAR data, and then linking those with the sea level rise projections in that area to identify areas at risk. And happy to share some images from the early work, but I think that's the slide I didn't get put back in here. So anyways, so the second piece of that I wanted to just talk briefly about is this idea of how our farmlands, so a lot of the work that we're doing is with farmers on these farmlands, trying to understand how are they responding to sea level rise, this changes in salinity. So you might have a farm, starts off in corn, for example. With the effects of salinity, you're seeing these declines in yield. We see farmers, you know, continuing to try to crop those in the same cropping systems that they have historically, sometimes trying to do different interventions to resist it, including things like putting in tide gates or berms. Also seeing farmers digging up some of the ditches alongside, throwing the soil up on top, making their fields super salty and hoping that the rain washes out the salts. So we've got a whole mix of different strategies trying to maintain the crops. We've also been looking at testing out different types of crops, alternative crops for planting in that region. And we actually see a lot of farmers shifting to things such as sorghum, or even shifting to more frequent soy, as I'm going to be talking about, because it's less susceptible to those salts. Alternatively, we see abandonment of agriculture, so just fields just left abandoned, uncropped, and we're sort of returning to a mixture of agricultural weeds and wetland vegetation. Or we can actually see actual restoration efforts, whether it's putting in freshwater wetlands, which is really interesting near saltwater entities, or implementing different herbaceous wetland restoration, perhaps through programs, either through federal programs or Trout Unlimited, that sort of thing. So depending upon the choices that farmers are making in response to these pressures, you end up having different benefits, both for the farmer as well as for society more generally. So the choice of adaptation or response strategies is going to affect the profitability of that land. The water quality impacts, like I said, it affects the mobilization of nutrients, carbon storage, flood mitigation, hunting and recreational values. That seems like a pretty big driver for perhaps shifting to more of a wetland, allowing for that wetland to come in, and also conservation biodiversity objectives. And so one of the things that I think is really important to think about is these are lands that are in transition. They are going to have to change. We have sea level rise. They are going to be different in the future. How can we use the science, the information that we're all gathering to help inform what that transition might look like in ways that are help the local communities, but also support the ecosystem service and other benefits that we care about in the system. And so again, this ties into how the economic, social, and environmental context are going to shape how this system responds. And so just one last study that I just want to highlight here is we've been looking at trying to use some remote sensing data. In this case, it's actually the USDA cropland data layer information to try to understand how farmers have adapted it in terms of changes in cropping decisions and land use in response to saltwater intrusion and sea level rise. And so we have 11,000 farm fields across this region. Data we're using from 2008 to 2021, and we're able to then classify the different types of land covers, both in terms of what crop rotations are being grown on these properties, whether it's a corn rotation, where corn is one of the more susceptible common crops grown on the eastern shore, whether it's other non-corn grains, or whether it's shifting to woody wetland, herbaceous wetland, grass pasture, forest, developed. So we essentially have classified all these fields according to their different rotations, and are then able to look at how the distribution of crops and land use varies depending upon proximity and different proxies for saltwater intrusion, so for the salinity of the area. In particular, we're relating it to the elevation with respect to mean high water levels. With the model, so we're using a multinomial logit model for those who care, but we're essentially developing a model that relates the soil and elevational and other attributes of the parcels to the cropping decisions, and then we can then run simulations to say what happens under different scenarios of sea level rise in these areas. And so what we can see is, for example, for this decrease in the amount of agriculture and corn rotations, and even a loss of just agriculture overall, so we're losing the non-corn rotations as well. And so in particular, we're seeing that at the lower elevations, there's a big shift from the more salt-tolerant crop, from the more salt-sensitive crops to the salt-intolerant crops. And again, a lot of shift out of cropland. And so we're seeing this increase in the woody wetlands and herbaceous wetlands, kind of highlighting, again, the ways in which these are pathways, these are avenues by which we can see this migration of wetlands inland as a response to that saltwater intrusion. And one of the other pieces that we've done then is say, all right, looking that forward, what does this mean for kind of expectations on probabilities that these different fields are going to be in different land covers in the future? And you can see the areas that are darker are the areas we're expecting to convert to some form of wetland in the future, and the yellow be the areas that are still staying in agriculture. So you can see a very strong change just over these coming decades that we expect based upon the what we've been seeing up until this point. And so we've been using a lot of this, again, as being driven by the conversations that we're having and a lot of wanting to try to know where to do outreach and where to think about planning and thinking about how things are going to unfold in the future and what are the ways in which information can help shape those future transitions and support the communities in these areas. And so, yeah, with that, I just want to wrap up by just saying, looking forward, I think it's really important, to continue our conversations where we're thinking about how we evaluate, as we gather information and we can get the science behind what these different trajectories could look like, and even how policy processes could get there. How do we evaluate where we're going in terms of what is it that we're trying to achieve with the policies that we're putting in place? Who's benefiting for how long, over this, as we're in this very non-stationary world? And again, just kind of figuring out what the information is, the science that's needed to get there. And the way I'm really glad that we're having this conversation that's bringing so many disciplines together, because I really think that's key for getting where we want to go. So with that, thank you.
Okay, thank you all for having me. It's really humbling to be here among such amazing researchers and scientists, and yeah, this is great and important work. So I'm Shellie Habel. I'm a coastal geologist and hydrologist for the University of Hawaii, and I work alongside Sea Grant as well as the UH Climate Resilience Collaborative. And what I mainly look at are inland sources of flooding from sea level rise, including groundwater inundation. So what happens when sea level rises is a couple different things happen with groundwater, as we've been talking about today. One is that the groundwater becomes more saline. Another thing that happens is the water table comes up closer to the surface of the land, so it decreases the unsaturated space that's available. That's really important to think about. We're not thinking about it as much as we should, because that's where our underground infrastructure resides, and it's critical to the functionality of our urban spaces. And another thing that happens is in our really low-lying places, we have emergence of the groundwater, so it produces like urban wetlands in these urban areas. And these waters are not pristine, as we're talking about, yeah? They're contaminated, and so they're entering some of our public spaces. And so our research group, we look at things globally and also statewide, but our main kind of laboratory is the Honolulu area. Makes for a really nice study area because this is our economic engine for the state. It's located at really low-lying elevations, so the groundwater is naturally very shallow, and we're already having impacts, so people are paying attention. They know this is a problem. And so when we do our research and come up with our findings, we get a lot of attention, and we're able to incorporate our findings into things like planning guidance and even some law. And you might know this already, but the Waikiki and Honolulu area, it was once a wetland. Actually, the name Waikiki in Hawaiian means spouting waters or spring. And that spring water was cultivated into rice paddies, fish ponds, callow patches, pretty heavily until the early 1900s, when large reclamation projects, they're trying to maximize the developable area, and they dredged material. You can see the dredge lines right offshore where they've dredged the coral. They dredged, and then they placed that material on land so they could develop. But do you think that the developers were thinking about sea level rise when they did these projects? Probably not, right? Certainly not, probably. But yeah, they did these artificial filling projects all across the entire Honolulu urban core, including hardening shorelines. And since then, we've developed really heavily upon it. And we don't think about it, but this urban network requires that underground network of infrastructure to support it. And there's just not that much space between the land surface and the level of the ocean. And if you can imagine groundwater extending in as a flat plain, that's kind of the best case scenario. You still don't have that much distance, right? And that's the best case scenario. So in Honolulu, we've been measuring ocean levels since before World War I. And over that time, sea level has risen over a half a foot. And just that small amount of rise has started causing problems in the form of direct marine flooding, storm drain backflow even during blue sky conditions, and really shallow groundwater and groundwater emergence in our really low-lying areas. So up in the left-hand corner, that's me in a basement in Waikiki taking a salinity measurement. And what I'm finding is that the salinity is very close to full ocean salinity, which is highly corrosive. And actually, there's a couple haphazard adaptation things going on in this picture. There's 3 different ones. I always tell students to pick them out. We can talk about that during the discussion, if you'd like. And here's another image of some groundwater inundation happening at the Honolulu Police Department. And this one kind of opens people's eyes who are from the Honolulu area because they know that the police department is located about a mile inland from the coast. And so this brings home the message that this isn't just an issue just directly adjacent to the shorelines, but we need to think about this in all low-lying areas in our coastal cities. So we've gotten ourselves into a pickle. We built a lot of, we built our economic engine in a very low-lying place where we're bound to have problems and are already having issues. But we're not alone. San Francisco did the same thing. They heavily built on artificial fill in marshlands. Boston did the same. New York City, Tokyo. And actually, we did a preliminary study looking at functional urban areas that host elevations less than 1.5 meters, and we found over 1,500. And so we took that 1.5 meters, we use that as a threshold both because right now, 1.5 meters of unsaturated space is kind of the point at which critical infrastructure starts to be impacted by that shallow groundwater. And also because by 2100, there's a potential for that groundwater to become emergent with 1.5 meters of sea level rise. But we still continue to build in these really low-lying locations. And so the problem goes on. Even in Honolulu, we continue to build. So us hydrologists, we're kind of trying to get at this issue of better understanding shallow groundwater and its impacts multiple different ways. So we are doing a bunch of modeling, validation of our models, monitoring, and incorporating those findings into tools that are used by policymakers and planning officials. And we also try to work with those folks as much as possible to direct our future research into things that can be applied directly. So just going through our modeling, researchers in Honolulu can kind of boast that we were one of the first to identify groundwater emergence as a sea level rise related hazard. Actually, those researchers were able to land a publication in Nature Climate Change. Not an easy thing to do. But their model, it was a 1D analytical solution. So it had its drawbacks. So we kind of followed upon that by producing a more robust 3D model with ModFlow. But then we recognized the fact that not all communities have the time or monetary resources to build these kind of models. So then we did a comparison between groundwater simulations produced with our more robust method and with the hydrostatic method. And the hydrostatic method is what like the NOAA Sea Level Rise Viewer uses and all sorts of different agencies. And they use it because if you have a good digital elevation model, it's simple to do. And this is a really painful study because one of these maps took a half an hour to make, the other one took years. And you can't really tell a difference, right? And that's actually pretty good for communities because they can get at kind of like a preliminary sense of how groundwater inundation will start to occur in their neighborhoods, as well as where critically shallow groundwater exists. And then one more study I think you guys will find really interesting. So this one, we produced different simulations of like groundwater inundation, direct marine flooding, and storm drain backflow, and we overlaid that on geospatial data for infrastructure, characterizing infrastructure locations. So what we found, or one of the most mind-blowing findings, was when we overlaid the groundwater simulation on the cesspool layer. And we found that at present day, over 80% of cesspools are likely inundated by groundwater, which means they're leaching untreated sewage effluent directly into the groundwater, and that effluent is likely making it to public spaces. So those are very strong words. And so we wanted to back it up. And so what we did was we worked with our geochemist friends, and we produced this paper. It was pretty cool. So we looked at our simulations of what locations in Honolulu likely are experiencing groundwater inundation at high tides currently. And then we went out there at high tide and measured radon, which is a tracer of groundwater. And we identified that during our high tides, the radon pulsed up. And also, as a sewage effluent tracer, we used caffeine, pharmaceuticals, and antibiotics to determine during these high tides that indeed this cesspool or this sewage contamination tracer was also pulsing up. And that kind of verified to us that indeed the cesspools or other septic systems are inundated with this groundwater and are transporting that contamination into the public spaces. Oh, and before I move on from that, I just want to say that information collected during this study is being directly applied as part of policy for cesspool transition. And then we're working alongside the Honolulu Board of Water Supply to do monitoring in our coastal spaces. So there's a ton of monitoring done for drinking water resources inland, but there's not a lot, or there's none, there was none being done in our urban zones because we don't drink that water. But we still need to understand the phenomena that's happening with groundwater inundation. And so we partnered with the Honolulu Board of Water Supply to install this coastal groundwater monitoring network. And the main point of that was to get high quality data to improve our models. So we did that, all good. But also, since we have the wells in there, we might as well monitor it to better understand how the tides, rainfall, various phenomena influence groundwater positions and salinity. So I'll just show you some of our data. This is, again, from the Honolulu Police Department, where I showed you the basement flooding that was happening. And so in blue, that's our groundwater elevations. In red, that's validated tide measurements. And in cyan, those are rainfall measurements from the Honolulu airport. So we were able to calculate tidal lag, tidal efficiency, and then we were able to strip the predicted tide from both the groundwater measurements and the tide data. And we were able to, so we were cleaning it so we could compare how groundwater tracked with background sea level. And there's an even higher efficiency there, which is expected. And then we captured a 50-year rain event and saw groundwater levels rise over a foot, which is important to think about because the closer groundwater gets to the surface of the ground, the more ponding and rainfall-related runoff you're going to see. Then also during that rain event, we saw something kind of interesting where the salinities peaked during the rainfall. At first it was kind of counterintuitive to us, but speaking with you guys, you probably know what's going on. So in these wetting and drying zones, salt crystallization occurs over time, and then you have a rainfall event, and that kind of flushes it out. And so you see a pulse in that salinity during those rainfall events. And we see that at a couple different locations. So moving on to tools that we're putting together. So we worked with folks at the annual review of marine science to put together a resource where folks could better understand these processes, impacts to our infrastructure, and as a bonus, we tried to work in management strategies that are being undertaken around the world. And so we looked at impacts to things like roadbed flooding. As groundwater comes up, it gets into the unbound base layers and starts to degrade that. It impacts our piping networks, including our sewer mains, our drinking water, and our drainage. And so we looked at that and kind of the impacts of that corrosion. And then we looked at impacts to our building infrastructure through corrosion, pressure-induced heaving from the tide going up and down, and then basement flooding. And so that resource was kind of a general resource that we hoped could be used along coastal cities around the globe. But we're also trying to produce tools for our local government. And so we actively, through our more robust modeling, put together maps of locations of critically shallow groundwater that's just barely, like almost emergent, where it just takes like a rainfall event for it to become emergent, and also locations where groundwater is already emergent. And then we consider sea level rise in 1 foot increments all the way up to 10 feet. And we post our maps on publicly facing sea level rise viewer tools, so anybody can access that data. And then just getting back to our comparison study, as painful as it was to produce, that was probably our publication that allowed us to get this data into things like guidance and law most easily, because while our robust maps are really great, we haven't made them for the entire state yet. They take a really long time. But we do have hydrostatic mapping for the state. And so guidance has been produced for areas that are shown to be impacted by hydrostatic flooding. And so in that guidance, because of the paper that we published, we were able to include language in there regarding what we know about groundwater inundation for those spaces. And we were also able to include wording in a couple of different laws, one regarding real estate transaction, and another one about environmental assessment permitting. And as far as future work, we're really excited to start working with the Hawaii Corrosion Laboratory. And so what they do is they make little things called coupons made of all sorts of different types of metals that our infrastructure is made out of, and they put them in different environments. And the submarine environment is one that they haven't gotten to yet, but they're excited to. And so we're hoping to replicate the environments we're seeing in our wells and to see how that is actually impacting our various infrastructure made of these components. And that lab is really well equipped, and they know all things corrosion. And then we're also really excited to work with our State Department of Health. And so there are thousands of sites of known contamination among the islands. A lot of them are coastal. And so we're going to work with them to look at areas of shallow groundwater and emergent groundwater with sea level rise, and how those overlay upon these contaminated sites to hopefully form like a triage for how to go about attending to these. All right. So that's your whirlwind tour through what we're doing in Hawaii, and I've included my contact information here. Just want to thank all my colleagues at the Hawaii Climate Resilience Collaborative and Hawaii Sea Grant.
So bring us home in this session here. I really enjoyed those first two talks. Really nice overviews of saltwater intrusion. I'm going to take a step back and really focus on one of the drivers of saltwater intrusion, focusing on sea level rise. I guess I should introduce myself. My name is Ben Hamlington. I'm a research scientist at the NASA Jet Propulsion Laboratory. I'm also team lead of the NASA Sea Level Change Team, so I like to talk about sea level, and that's largely what I'm going to cover. But I'll try to articulate some of the timelines, some of the projections, and what they mean for what we're going to see along our coastlines and impacts coming up in the next few decades here. All right, so the intent of this slide is I think, just to reiterate some of what we've already heard today. NASA is measuring a lot of the Earth climate system from space. We have a lot of satellites up there measuring a lot of different parameters. Looking across this full set of parameters and these different sensors allows us to get a good understanding of not just the physical processes that are occurring, but how they combine to drive impacts as climate change continues to progress. And I'm going to focus on one of these in particular. I'm not going to ask you to identify it circulating around there, but one of our core observational records is from satellite altimetry. So satellite altimetry is basically how we measure the height of the ocean from space. So from over 1,000 kilometers up on orbit, we can measure the height of the ocean down to about a 1-inch accuracy. So incredible accuracy from up in space. And one of the real programmatic success stories that we've had here at NASA is that we now have a over 30-year record of satellite altimetry measurements of the ocean surface. So you can see this is the Sentinel-6 Michael Freilich satellite, our one that we launched most recently, and this 30-year record. It measures a long track, so basically it's measuring the height of the ocean directly below the satellite as it orbits the Earth, and every 10 days you get a complete view of the ocean. You can fill in some of those gaps with interpolation, and you can get a complete view of the change that's occurring on a variety of timescales. So not just the change that's occurring over 30 years, but also the change that's occurring over the course of weeks and months. The reason I point this out, it's going to be relevant when I start to talk about some of our more recent observations that we rely on now to fill in some of our gaps. But again, we have this now 30-year record, and we can do a number of things with this record to really understand exactly how sea level change is occurring. One thing we can do is take those observations, see if this rotates. Take those observations, and we can see the change that's occurring across the globe and how that varies from one location to the next. So this is just the sea surface height change occurring over those 3 decades in units of centimeters there. You can see in general the sea level is going up everywhere. Some areas going up a little bit faster than others, but these satellite altimeters give us a good view of what's happening on these regional scales. The other thing it can do is tell us what's happening globally. Right? So we can take all those observations, we can average them together and see how global sea level is progressing. Really good indicator of our Earth climate system. Global sea levels obviously respond to both the warming of the ocean, so the water expands as it warms, and also the melting of the cryosphere, the ice sheets, and how that then contributes to the ocean. So this animation here is just showing the progression over time. So it's going to plot each year. I think we've seen similar charts like this for sea surface temperature or surface temperatures, but this is a new one we've generated for sea level. So you can see the seasonal cycle over time, and then the increase that's occurring. Oops, sorry, I clicked. I was trying to get rid of the bar at the bottom. And then the increase that's occurring over the 30-year records. And we've seen about 10 centimeters of increase during the 30-year record. It's going to do a nice thing where it rotates here. And shows us the change over time. So we have those up and down, those annual changes that are occurring as part of the seasonal cycle, and then we see this long-term shift that's taking place. So about 10 centimeters over this 30-year record. And we can do a number of things with that record. We can start to say something about the trajectory of sea level rise. So a lot of times we talk about the rate of sea level change over those 3 decades. It's about 3 millimeters per year, but that's only telling part of the story. So sea level is not just increasing at a constant rate, we're putting our foot on the gas pedal and it's actually accelerating. And we can start to see that with the satellite altimeter records that we have. So by fitting that trajectory at any given time on that trajectory, you can estimate the current rate of sea level rise. And based on that trajectory, we're seeing about 4 millimeters per year of sea level rise now. If you go back to the beginning of the record, about 2 millimeters per year. So we've seen about a doubling in the rate of global sea level rise over this 30-year record. We can also say something about where that record might head. If that trajectory continues out into the future, we can say something about what we might see in the coming decades. We can use that as a comparison to the models, which I'll show on the next slide. The other point I want to make here is that we can also track the change that's occurring from year to year. So you can see in 2023, we saw about 0.76 centimeters of sea level rise, largely due to the El Nino that took place. So we see a temporary elevation. So we have all these other variations, which are very important if we think about coastal impacts and the flooding that will potentially occur from year to year. But we also get this assessment of what's happening over much longer timescales. All right, so if we now compare this to modeled projections. So here on the left, I'm showing the projections from the recent AR6 report. These are global projections organized by warming levels. So you can do something similar for the SSPs, the shared socioeconomic pathways. But here I'm organizing it by temperatures. And those bars on the left show you the projected amounts of sea level rise at different times under different scenarios. So our observed sea level change, global sea level change over the past 3 decades, about 10 centimeters. And then I have that projected value, and you'll notice it's not linked to any particular temperature or SSP. The range across our different scenarios just out the next 3 decades is very narrow, right? So regardless of what we do, we've almost locked in about 20 centimeters of additional sea level rise on a global scale. So we have 10 centimeters over the past 3 decades. We're going to see almost double that over the next 3 decades. As you start to look further into the future out to 2100, that's where your warming, your emissions dependence really starts to come into play. The degree to which we can limit warming really affects what we might see. In the worst case there at 4 degrees C of additional warming by 2100 with some of the potential contributions from rapid ice sheet loss coming into play, that's where you start to see the potential for much greater than 1 meter of sea level rise. Okay, so to bring this back down to a level I think that is of more interest to what we're talking about today, what can we start to say about how this is impacting globally? So those same global projections, there's a regional pattern associated with those. Here I'm again showing that rotating globe I showed earlier, the amount of sea level change we see from satellite altimetry. Here I'm just showing in a map. So this is the amount of sea level change that we've seen over the past 3 decades in centimeters. Again, lots of the similar orange yellows as the color bar chosen here. Roughly around that 10 centimeters, some locations a little bit more than others. If you look at the east coast of the US and the Gulf Coast, those are areas where we've experienced a little bit more of sea level rise than other places. But if we then look out the next 3 decades, and actually a little bit less than the next 3 decades, this is the projection from 2023 to 2050 for that mid-range scenario. And in most of these locations, it's just plus or minus a few inches, depending on the different scenarios we have. So this is giving a clear indication of the amount of sea level rise that we're going to see in the coming decades on the order of 20 centimeters or greater. And to show a slightly different version of this, the color scale has changed here, but here I'm showing the projections out to 2100 for these different scenarios I talked about. Again, just noting that the emissions matter in the longer term. So this is looking at 3 degrees C. This is roughly the trajectory that we're on now with future sea level rise, or with warming and the sea level rise we might expect to see. And here's our worst case for high amounts of warming and rapid ice sheet melt. And then just one other way of showing this is just to convey that narrow range we see in 2050 across the different scenarios. That 20 to 30 centimeters is really an important factor. And then as you go out further into the future, you start to see the spread of the different scenarios. Okay, so I've talked about projections. I've talked about these large scales. What does this actually mean for coastal locations? All right, so 20 centimeters may not seem like a lot, right? What can 20 centimeters do in terms of driving additional flooding? So I've done this little cartoon, but this is an actual tide gauge record. The high-frequency tide gauge measurements from Kiribati. It shows one particular tide gauge in the Pacific, a low-lying island impacted by sea level rise. And I have, so again, it's a cartoon, but it's using actual data. That threshold is the roughly 2-year flooding threshold in black. And you can see over the past 30 years, we've just had a handful of flooding days that have been experienced, right? You might have some flooding associated with storms that come through, large natural variability that happens. But if we just shift that upwards by 20 centimeters, this past record by 20 centimeters, this is what it would look like. right? So it's not a slow increase that we're seeing. We're reaching a threshold, and we're so close to the flooding threshold in many of these locations, especially low-lying locations, that you have an order of magnitude increase in the amount of flooding you'd experience with just 20 centimeters of sea level rise. A way to think about this, if I'm carrying a glass of water, it's half full, I'm kind of sloshing it around, you're not really worried about that water spilling over the top. If I get that water very close to the top, that same sloshing is going to start to spill water over the top, right? You'd be much more concerned about it. Similar thing is happening here. We're filling that glass up towards the top. We're still sloshing around the same way that we always have, and now we're causing flooding to occur. So if we open this up a little bit more, so this is, these are tide gauges in the Pacific. So these are Pacific Islands. These are the number of flooding days that have occurred in the past 3 decades on average. So I'm showing the average flooding days per year for a given year. Some years could be a little bit worse, some years a little bit better. If you have an El Nino or La Nina, that's obviously going to shift these one way or the other. But in general, most of these locations are seeing less than 10 days of flooding per year at high tide, again, driven by storms. This is work done by a colleague at the University of Hawaii, Phil Thompson. But if we take, again, that 20 centimeters, we add it on top, that's roughly what you get in 2050. This is what it then looks like. So an order of magnitude increase in the amount of flooding that some of these locations are going to experience. So instead of having to deal with a handful of days on average of flooding, you're going to be dealing with it almost every other day, or potentially, as we go out a little bit further, at every high tide. Right? So it's a very immediate problem. We think 20 centimeters, and we know that when to expect that 20 centimeters to occur is not that much. But when we think about the impacts that are going to be experienced, the saltwater intrusion that was talked about earlier, the flooding that we see, the impact of that water on land, it really is a huge shift that's going to take place. And then one other way of looking at this, so NOAA keeps track of the different flooding events. So they release a report every, I think, quarterly now, talking about the number of high tide flood events that have occurred. They made this assessment as part of a recent interagency technical report, noting that with an additional foot of sea level rise, that's more accurate to what we're going to see in the U.S. By 2050. You're going to see this regime shift in terms of the flooding that's going to occur. So the minor flooding that we experience now, that roughly 3 events per year, in 2050, that's going to be the frequency at which we experience the moderate events. Same thing, the shift from major to moderate. So you're just shifting everything upwards and experiencing the events with much more severity and much more frequency than you have before. Okay, so just one note on, I'm going to bring this back to the saltwater intrusion, just to make the point. I think the previous 2 presentations went through this in much more detail, but using a simple 1D model, I think that was similar to what was referred to in the previous presentation, we can come up with a screening level assessment of saltwater intrusion based on these projections, based on our understanding. So this is work that is being done under support from the Department of Defense, looking at trying to understand exactly what parts of the globe and, say, military installations on a global scale are being impacted or potentially impacted by saltwater intrusion going forward. You can see quite a bit of spatial variability. This is under projected changes in both sea level and recharge going forward. But again, we know that the sea level that's going to increase is going to drive these same impacts to increase as well that the previous 2 presentations covered. Okay, so I'm going to finish up by talking about our newest satellite mission. If I can click forward here. So our newest satellite mission is the Surface Water and Ocean Topography mission. So SWAT is providing, it's kind of skipping on me. Okay, I don't know. Trust me, the animation should be better than that. NASA wouldn't put out anything, I guess, that doesn't look better. Okay, but so SWAT is measuring surface water on a near global scale, right? So this is a big step forward. It's not just measuring the open ocean. It's not just measuring surface water and land. It's measuring both of those and also at the interface. So it's providing us measurements along the coastal interface. It's doing this in a swath. So when I talked about the along track measurements of our previous generation of satellite altimeters, SWAT is actually doing much better and allows us to see the ocean in much greater detail than ever before. So here we have this view in Central America. I just plotted a few of the tide gauges that are there, but over the course of 21 days, this is the picture that SWAT will fill in. You see a little bit of the trackiness there just associated with the repeat orbit of SWAT and coming through and making these additional swath measurements. But now we're starting to fill in these gaps. It's a little difficult to see too, but you can actually see that the SWAT is providing measurements into these coastal areas onto land and really seeing the complete view of surface water. So it's filling in these gaps, much higher resolutions than ever before. I'll show in just a couple slides here that we're getting resolutions down to the order of less than 200, 100 meters. Okay, so this is the, let's see if this plays. My goal was to see how many animations I could get into one presentation. Okay, I'm not sure this one's going to play. Failed on the last one. But so SWOT is providing this global view of the ocean and also on land. The thing to note here is that it's seeing these features in the ocean at much greater detail than ever before. So we're able to track these mesoscale eddies, movement in the ocean, these shorter term ephemeral features that we know are important to the transport of heat, carbon, other things in the ocean. We're able to see those with SWOT in new detail, more detail than ever before. But I want to talk a little bit about what SWOT can do both on land and in coastal applications. This is just a cool study, and this was actually a part of a press release that NASA just put out today. But this is, some of you may have seen the reports on Badwater Basin and Lake Manly, the temporary lake that sprung up with the remnants of Hurricane Hillary back in 2023, in August of 2023. So Badwater Basin filled up this Lake Manly, as it's called, filled up back then. And over the course of the successive months, there were additional rain events that caused it to refill. So we would have periods where it would start to evaporate and drain off, and then other time periods where it would fill back up. And that's really showing the progression, the level of detail that SWOT is able to provide in some of these locations. And taking the DEM, the elevation in this location, we can subtract that out from the SWOT measurement of water height and actually measure the depth. So we can actually find depth profiles across this, this lake over the course of these few months. So again, much higher resolution and much greater detail sampling in locations that we haven't been able to before. And then one last application here, and I'll wrap it up. So this is another study, just a quick snapshot of what SWOT can do in coastal regions. So this is up north in the coast of California, near Manchester, California, and you can see Point Arena right there. The SWOT was able to see some of the flooding that occurred on land, both the flooding that occurred in some of the rivers, but also some of the flooding driven by the coast, so the higher water associated with these storms. So on the left here, this is kind of normal conditions pre-storm or storm-free. On the right, we were just lucky enough to have an overflight of SWOT at the exact same time that the storm was impacting the coastline in this particular area. And you can see some of those flooded areas that are pointed out. So with this data, there's a high potential there to be able to use it for trying to really advance our understanding of flooding at the coast, where water goes when it starts to flood, potentially to be used in models of saltwater intrusion as an input or a boundary condition. So again, a huge opportunity launched as part of this, this most recent mission. And I will leave it there.
So I have a question for Ben. Please forgive me if I'm not being scientific. So I keep seeing in the social media that people talking about climate change, but they say this is not about carbon emissions. So I don't know how the NASA scientists say about this. How we make proof that climate change is actually related to the carbon emissions, because I think this is really important since you have shown that climate change has caused the sea level rise, and if we can solve this with controlling carbon, then probably this is an easy path we can do. But if climate change is just a natural process of the Earth, then maybe we should learn to adapt to this issue. So what do you think?
Yeah, I mean, I think the sea level rise or the climate change we're seeing, I mean, it's directly linked to the increase of greenhouse gases in the atmosphere. We see that through models, we see that through our observations. I mean, I think it's very definitive. Whether there are still some who are not convinced by that, I don't know. Maybe that's something we should continue to work on with communications, but it's unambiguous as to what's causing the sea level rise and climate change that we see. I don't know if that's exactly answering your question, but...
So my question is for Shellie, and to some extent for the first speaker as well. So I was thinking Honolulu looks like Amsterdam. So in a certain sense, what I'm trying to understand is, and if we think about all these global cities, are all global cities that are along the coast essentially going to start ending up being behind levees, and we're just going to adapt this infrastructure because there's large numbers of areas which have been sort of on the boundary of salt intrusion, including actual areas as well. And the question is there some way we can learn about places that are sort of much more marginal, much more sensitive to this, to thinking about how we in the US, for example, adapt? And I don't know which one of you wants to tackle that question.
I can try first, yeah?
Sure.
So I think there is that knee-jerk reaction of like, oh, we'll just attend to it with levees and pumps. That's what Amsterdam does. That's what New Orleans does. But I think there was an article that came out that said it costs like $3 billion to keep New Orleans dry. And it didn't even work during, it's only as strong as its weakest point, right? Because like when Hurricane Katrina came by, the levees broke and it flooded anyway, even with all that money put into that infrastructure. Plus, I think Amsterdam and that area has a problem, even though they've been really good at dealing with groundwater concerns for probably hundreds of years. They still have a problem kind of chasing their tail with like when they pump, subsidence happens, and that leads to structural impacts around that to infrastructure. And also when you have subsidence, that's a relative increase in sea level rise in that area. And so they're kind of chasing their tail with regard to like, okay, well, attend to this problem, but the attending to the problem is making the problem a little bit worse. And so actually in our review paper, I think that's one of the bulleted conclusions. I tried to like lay it out in clear bullets, so you'd really get take-home messages. And I think my very first bullet is avoid the knee-jerk reaction of just doing the pumping and the placing levees.
Yeah, I guess I'd just add to that, a lot of the rural agricultural areas where I work, that's unlikely to be viewed as a cost-effective solution where you don't have that same level of very expensive, long-lived infrastructure. And yet that actually is then some of the places where you're seeing a lot of the big impacts in terms of what kinds of, like the vulnerability of the different communities that are being affected by this. And then just, again, the wall, that there's always some sort of spillover effects to adjacent areas. And so you're, in that sense, the same sort of plugging one hole and can make things worse elsewhere.
Hi. Thank you very much for the talks. Ben, this is a very specific question for you. SWAT, can it see the salinity change as you move from the seawater into the surface water, the freshwater? No. Are there techniques or opportunities to do that using remote sensing, either on the surface or even more curiously in the groundwater?
Yeah, I'm not, we do have observations that measure salinity changes, or systems that measure salinity changes. I'm not sure what the resolution of those are at the coast and the level of detail they can measure. So yeah, I'm not going to give you a perfect answer other than we can measure salinity from space, and we do, but I'm not sure what the resolution is.
So I was sort of struck between the example of kind of what happens to the vegetation in Maryland and the vulnerability of Honolulu to sea level rise. And you almost have a kind of form of strategic retreat going on with the crops, right? The crops, you just can't grow them, and unless you do some sort of, injection to keep the sea level out, and it may not be worth it for some crops, you're not going to do anything about that. They're either going to retreat or go someplace else. But the one that kind of takes your breath away is Honolulu, because the built environment, good luck trying to strategically retreat that environment. There's no way we're going to be able to do it. And what's not in the hydrostatic model, but I know you are aware of, is the possibility of a hurricane. Instead of going north, coming down to Honolulu. Do you model what that potentially could mean for downtown Honolulu and Waikiki?
I don't personally, but there are hurricane modelers at SOEST. And Also, part of the monitoring that we do is to capture events like that and see what it does to the groundwater. We've already caught a tsunami. That was pretty neat. But as hurricanes roll by, we'll be able to capture that.
I would think from a policy point of view, this is where the segmentation of different research agendas may be getting in the way of presenting the urgency of thinking about strategic retreat or even recovery. Even if you don't want to do that, what are you going to do if you get that storm flow, that hurricane? That's not something we have to worry about in San Francisco at the moment. So we can just deal with nuisance flooding. But when you get that combination of the hurricanes that people are seeing down in Florida and elsewhere, combined with the vulnerability of your community right there, it seems to me policymakers have to understand, even if they can't do the strategic retreat, they should be preparing for the type of disaster that might come in terms of the water supply, in terms of the infrastructure. I mean, look what the fires did. Look how devastating it was. So I would hope that, some of this stuff could be brought together, because we're probably not going to be able to do strategic retreat in extremely expensive built-up areas. We're probably going to have to endure the disaster. And so it seems to me we should be fully informed about what we might be dealing with. Just a comment. Yeah, but I do think that trying to put this is why having people from different areas together might come up with better policy framework to catch the attention. Gets back to Megan's question about how do you get people with information to actually think about things. And if it's presented to them in different slots, they're not as likely to see the impact in terms of the economy, in terms of the recovery, in terms of the disaster. So just a suggestion.
Just an anecdote to that. So before I came to California, I lived in Norfolk, Virginia, and I was sitting in a meeting talking about sea level rise and some of the projections with some of the power companies there. And they showed some of their models for different scenarios, looking at Category 1, Category 2, Category 3, coming from different angles. And then they just stopped. And the question came up, well, why aren't you modeling for a Category 4 or something higher? And I said, well, basically the whole area would be completely underwater. There is no recovery plan that you can have in advance. So I think that is some of the challenges they're very localized challenges. I mean, it's how flat an area is, the evacuation routes, things like that. But the ability to plan for the different possibilities, I think, is still an ongoing struggle.
I might be actually interested in asking one follow-up question, and then I'll let Laura have the last question after that. So one thing that struck me, Becky, when you showed that is I feel like a lot of what I've seen in terms of sea level rise has been from the perspective of homeowners and moving more of that urban infrastructure, as Bruce said. And so the agricultural component of that, I think, is sometimes received less attention. On the policy decision-making side, are those two sort of information about home ownership versus agriculture, do they make decisions in the same way, or are there conflicts there in terms of how those decisions interact with each other?
That's an interesting question. So, the policy context, I would say, is different. What's going on, a lot of Maryland, like where I'm working, it's, Maryland Department of Planning does, they're the ones who are developing the state saltwater planning for the state. But it's, Maryland Department of Natural Resources and Maryland Department of Ag who are focused on a lot of what's going on in these coastal areas. And there's a lot of intersection between sort of the national policy or incentive programs for making these transitions. Most of those are not really being framed, I would say, within the agricultural context, in the context of sea level rise or saltwater intrusion. And one of the big challenges is that, and where a lot of the work is focusing right now, is how do you design easements, for example, in these or other incentive programs in these areas where we know we're going to see transition, where typically, for example, an easement, you have put a conservation easement in place, your goal is to try to keep it the same and keep it pristine, but you're going to have these changes. And so there is, I'd say a lot of the policy work is more in that context, but it is very different than in the case of long-lived infrastructure where there's people in harm's way. So it is a different policy context.
Yeah. Okay, let's take one more question and then we'll break.
Thanks. This will be quick. This is just a question for Ben about the SWOT data, which I find to be so fascinating. And as a social scientist, there are a lot of social science questions that I would love to use it for, but those social science events are like some of these legacy events that were discussed in the keynote, policies that were implemented in the last several decades. Is there any ability to sort of make estimations from historic timeframes, like using these new and incredible and improved satellite measurements?
Yes, so to kind of be see how they relate to measurements we made in the past.
Yeah, and try to calculate like with better data, some surface water elevations.
Yep, absolutely. I mean, I think it's going to give us observations of like foundational baseline data in areas where we haven't had it before. So yeah, to have those measurements available to us, I think will help improve our understanding, provide additional context for historical observations. So I do think that's a rich area of research and study.
Okay, that concludes this panel, and I think we are scheduled for a coffee break. Hannah, is it just in the back here? Okay, so just in the back. I'm sure the panelists will be happy to follow up if you have any other additional questions. Thanks.